Hello everybody. I decided to re-record this video on how to do the data analysis for the Kinetics lab because the original video I recorded during the lab itself was kind of choppy and hard to follow because I kept on stopping to help people. So the video you're going to watch now, or you're going to see now, will be straight through on how to do the data analysis for the Kinetics lab and for how to answer the discussion questions that we have at the end, right? So the first thing you need to do, of course, is um, make sure that you have all of your data inputted into the Excel file, right? You should have three sets of data, right? And I don't know what happened there. There we go. You should have three sets of data, right? One for trial one of the zero point 0.05 molar sodium hydroxide, one for trial two, one for the trial two for the zero point 0.05 sodium hydroxide, and then one for the first trial, or the only trial you had for the zero point 0.1 molar sodium hydroxide. And I'm not really sure why I did it this way, but I'm going to fix it right now. It should be 0.5, sorry, 0.05 molar with an M in there. So I'm going to go ahead and fix that real quick. Whoops. And then like that. Okay. So I'm basically just going to go through the instructions of the lab and do what it tells me to do. Okay. And you can do this too. When you go through the instructions of the lab you have, right? And it says under data analysis for part one, you need to plot the 1 over CV concentration, right? Or 1 over uh, crystal violet concentration versus time in minutes, right? And so uh, remember that when you plot the 1 over CV concentration versus time, right? And you get a straight line, that means that it's a second order reaction, okay? The kinetics are second order for with respect to the crystal violet or the CV, right? So the first thing you've got to do here is you can't plot 1 over the absorbance. You've got to actually plot 1 over the concentration of a crystal violet. So the first thing to do here is to insert a new column, and you can just click on C right there, and then go insert, and it will insert a new column. I will also move this over here like this too, so that the title of that column can go all the way across, like that. And then I'll label this concentration, or sorry, this column, 1 over the concentration of crystal violet, or CV. Okay? And so now you may be asking yourself, where do we get these data to put in here, right, in this column? Well, we've got to use an equation, right, that we talk about earlier in the lab. It's actually in the lab handout, right? But I'll talk about it here for you so you know that this is what you need to use to figure out the concentrations from these absorbances, right? So let me bring up the whiteboard real quick, okay? And so there's an equation known as Beer's law. Oh, let me make sure I'm on the writing thing. There's an equation known as Beer's law, and Beer's law says that the absorbance equals B E C, okay? And so the absorbance equals BEC, right? And based on the information you have an absorbance already, right? Those are all the absorbances that you took, you wrote down as the time was going by, as the spec 20 as the reaction was progressing inside the spec 20, and you're writing down those absorbance numbers every 30 seconds, right, for 30 minutes straight. Um, and then what you're searching for is C, because the C here is the concentration, right? Uh, B here is actually known as the path length, and that's the path length um, uh, uh, of the cuvette that you used when you put into the into the spec 20, right? And if you look at it, you could probably tell that path length that the light travels to go through the reaction medium uh, with the cuvette and the spec 20 was about 1 centimeter. Okay, and then this cool little E looking thing here is actually known as the molar absorptivity. Absorptivity, right? For crystal violet, right? Since we're doing the concentration of crystal violet from its absorbance, okay? That's a value that you can look up, and when you look it up, the number is that equals 5.0 times 10 to the 4. And it does have units too, but we're not too worried about it at the moment. But the units are uh, m to the negative 1 and centimeters to the negative 1, right? So the first thing I would probably do just to make life easier on you is actually convert this number here from scientific notation to a regular number, right? And that's as easy as moving this decimal point right here 4 spaces towards the 0. And so you get the number of 50,000. Okay? So that's how you're going to do this. That's how you're going to figure out the concentration for each of these absorbances, right? Because A equals B E C, and all you have to do to solve for C is divide both sides by B E, and so now A B E equals the concentration, right? So that's the formula that you're going to put into the Excel file at the very top of that column, right? So to do that, what you're going to do is I'm going to actually move my thing over just a tad. Whoops. See if I can get it here going. So we can see both at the same time. There we go. And then there's the Excel file. We'll move that over just a tad bit too. So here's A equals BEC for the absorptivity, right? Here's the 50,000 for the molar absorptivity value, and then the path length is 1 centimeter. So in this very first cell right here, that's right under the 1 over CV, what you're going to do is you're going to type in equals, right? And then 1. Oh, I'm sorry. Actually, we forgot to do something. We actually need to get the concentrations first, right? So what I would do is actually insert one more, right, and actually make this concentration of CV, like that. And then now we type in the equation for the concentration conversion from absorptivity. So that equals C, right, which is over here, C right there, right? And so C equals BA divided by BE, right? So all you have to do now is click on the absorbance value, which in this case here is cell B4, or the value 1.05, right? Type in divide, and then inside parentheses, put in the B and the E values, right? Which is for B, it's going to be 1, and then times 50,000. Oops, like that. And remember to close the parentheses. Okay, and it's important, right, for you to put these in parentheses because you need to do this first, inside the parentheses first, and then have that number, have B4 or the absorptivity divided by that number after you've done the parentheses first, right? So you press enter, and that gives you that number right there, that value, the concentration. So that's the concentration of crystal violet at time 0, right? 0.00000, wait, 0.00021. And then you can actually populate the rest of these cells right here for the concentration for the rest of these absorbances, right? By first highlighting that equation, the cell where that equation is, and then putting the cursor, the mouse cursor, over this little square right here until it turns like into a black cross, and then click on it and then drag down. And I'll tell you right now that it's a lot easier doing this with a mouse than it is doing it with a touchpad. So if you have a mouse, you should use a mouse. Okay. So what I did there now is populated the rest of the field uh, of the concentration of crystal violet with the concentrations of crystal violet for each corresponding absorptivity or absorption. Okay. So now that I have that, I can finally move over and do the calculation for the one over the CV, right? Because remember, if I do the calculation for one over the CV concentration, crystal violet concentration, and plot all those against time, right? And then that graph turns out to be a linear graph, then I know that this reaction is second order, okay? Because 1 over the concentration of CV corresponds to a second order reaction uh, if that graph is linear, right? So now what I need to do is do this. Click inside the cell again, and I'm going to type in equals, and then this time it's going to be 1 divided by, and then you click on the cell of the concentration, the corresponding concentration, right? Which in this case was C4. Press enter, and then that gives me the value for 1 over CV. I'll do the same thing again where I highlight that equation, the cell that has that equation, roll my mouse cursor over to the little tiny square at the very bottom right hand corner of that cell, click on it, and then drag all the way down to make it populate the rest of the cells. And so now I have the values for 1 over CV, right? So I'm going to zoom out a little bit now so I can actually graph this, right? So I'll go up here. I'm actually going to make this bigger now so you can see it better. And then I will go over here and change the view to, let's say, zoom to 100. Okay, that's good. Now you can see my time and my 1 over CV. So now I want to graph it. Pretty easy to do that. First thing I would do is get myself over to the insert. Oops, not that insert, this insert right here. Okay, and you can see my graph options are right here. Okay, so first thing to do is highlight the time. And then you need to highlight the column that has the 1 over the CVs. Okay, so to do that, to highlight more than one column at the same time, if you have a Mac, all you have to do is hold down Command while you're doing it, while you already have the other one highlighted, hold down Command, and then click on the column you want to highlight and drag down to highlight the entire column. Again, this is much easier with a mouse and a keyboard than it is with a touchpad. So that being said, if you have a PC, you're not going to use the command button, you're going to actually use the control button, okay? And do the same thing. So now you have both of these columns highlighted, right? You can go back over to your insert graph options, and the graph you'll be inserting is this graph right here. It's the XY scatter plot, and I would pick the very first graph, right? And it automatically graphs it for you that fast. Notice, right? And you can see here that my graph is actually kind of curved. It's not straight. So just looking at that right there makes me think that it's not going to be a second order reaction. Okay. Now, again, my data is made up. I don't have real reaction data. Yours might be different, right? But my data here, my fake data here shows a very curved line, right? Well, how can I ensure that it's a curved line? Before I actually show you to do that, how to do that, we're going to make multiple graphs here. So I would go ahead and just title my chart, right? And just double click on the chart title and type in uh, this is the 1 over the concentration of CV, right? Uh, versus time, like that, and while we're at it, we can make it look super pretty too. One of the things I don't like about these scatter plots is that it has these grid lines in here. So I always get rid of the grid lines because the grid lines aren't pretty to me. We'll get rid of the grid lines. And the other thing you might want to do too is maybe make your x-axis a little bit darker. It's it's a little bit faint to me looking. So I'm going to make this bold so I can see the numbers a little bit better. You can make the numbers bigger too if you want, since there's plenty of room. So you could just go through and make it like maybe 12, right? So you can see them better. I'll make the font of that one down there as 12, so you can see that better, right? So now you can see the graph a little bit better. Another thing I do too on this graph, and this is good for you to know, so when you write your report, you have nice labeled graphs. A graph should always have the title and the axis names, and if necessary, a legend, right? So one of the things you can do now is click on the graph, and you go to after you click on the graph, you can go to chart design, and after you go to chart design, you can go over here to the left-hand side, and on the left-hand side, click on that little arrow there, and you can add some chart elements, right? The chart elements you want to add here, you've already done a chart title. So one of the things you might want to add is a primary horizontal title, right? So that adds that in there. And I would call this time, right? And never forget the units. So time in seconds there. Still looks a little faint to me. So I'm going to make that bold and a little bit bigger. We'll go back home, make it bold, see, and make it a little bit bigger. 12, right, like that. Very nice, very nice. Okay. And then on this side, you can do the same thing again for the y-axis. You can go over to chart design, go to chart elements, and you're going to do axis titles. And now you're going to do the vertical, the primary vertical, right? And this is just the 1 over, oops, let me just get rid of the what's already there, the default that's already there. So 1 over CV, concentration of CV, like so. Oops, sorry about that. Moved my thing a little bit too far. Okay. And I don't know why I did that there. I actually put a braces there instead of a bracket there. So let's get rid of that and put in the bracket right there, okay? Again, it's a little hard to see, so I'm going to make it bold and make the font 12 for that title. Right, there we go. Now we can see that that says. And then the other thing I'll do too is I'll make the title of the entire graph a little bit bigger as well, bold it. And since it's the title of the whole graph, right, like that. So, and I like it when students have their graphs looking all consistent and stuff too. One of the other things you can do too is these axis lines are really thin right here. So if you click on the axis line, just like I did there for the y-axis, you can come over here to the line, right? And right now the width of the line is 0.75 font, right? Or 0.75 point, right? And so you can actually make it thicker just by moving it up like this. See, I'll make it up to go to 1.5, and you can see now that the line is actually a lot thicker. The other thing too, it's gray. I don't like that it's gray. I can change it to black over here. See, now everything looks like you can read it again, right? We can actually read it better. Let's do the same thing with the x-axis. We'll bring that up to 1.5, and then we'll also change the color to black. See, now the graph is so much cleaner. You can see the lines a lot better, right? And it just looks cleaner to me. Okay. Um, so now that we've I don't know why I went through the aesthetics of the graph before I actually got to talking about how to make the graph actually give you good information. So the next thing you've got to do here, right, is to actually determine whether or not you think this thing is a straight line. Just looking at it, it doesn't look linear to me. Uh, it looks kind of curved, right? But how do I know for a fact that it's not linear? Well, I can click on one of the dots there, right? I can click on one of the dots, and then when I right click on it, right, I can do add a trend line. And when I add a trend line, you see here the trend line is going right across these dots. And the thing that you need to add to this trend line to help you decide whether or not this is a linear reaction, right? Uh, or sorry, if the graph is linear for the 1 over the concentration of the crystal violet, is you have to first of all go over to the graph options, make sure that you are over, or the trend line options, make sure that you are linear in linear mode, and then you need to set an equation, display an equation on the chart, and you need to display the R value, also the R squared value in the chart. And there it is right there, right? Still a little bit kind of small to see there, so I'm actually going to close out my trend line options here and maybe zoom in a little bit so you can see it a little bit better. Let's go back to 150 maybe. There we go. All right. So now you can see it a little bit better. You can also make this look better too by going back to home, right, and highlighting that, clicking on that box there, and you can make the font 12 and you can make it bold and you can read it a lot better. See? So what I have here now, right, is an equation of the line, which is that right there, okay? But then the thing that I really want to look out for is this right here, the uh, r squared value right there, right? That r squared value. It says it's 0.964, right? And if you recall from lecture, the straighter the line, the closer it is to 1, right? And even though that looks like it's a straight line because it's pretty close to 1 with the 0.9643, when I say straight line, I mean like, 0.99 or something like that, not 96. So to me, that's not a very straight line, okay? So then what that means is that since we don't think that this is a second order reaction because the line, the graph for the 1 over the concentration of CV isn't linear, so we don't think it's a second order reaction, we've got to take it a step further now, right? So I'll go over here and I will insert like so, right? Click on the E, click on and then hit insert. Right click on the E and hit insert, right? And now we're going to see if this is actually a first order reaction, right? Because in a first order reaction, the graph is linear when you graph ln, or the natural log of the concentration of crystal violet, like so, right? And so now that I have that, I've already done most of the legwork here because I've already got my concentration figured out. All I've got to do is the same thing I did when I did 1 over the CV concentration. Here, instead of doing 1 over CV, we'll do equals, right? And then for the equation uh, in Excel, the natural log is actually capital N, capital L, capital N, like that. And then the value actually goes inside parentheses, right? So you open parentheses there, and notice it gives you a little hint there to put a number there. And be sure not to put in the number that was for the 1 over the CV. You need to put in the number for the concentration, right? So it's going to be this over here, C4 again, all right? Be careful with that. Be careful with that. And then you can close the parentheses and press enter, right? After that, you can populate the rest of the fields by putting your arrow, your cursor on that little square in the bottom right-hand corner of the cell and dragging down, like so. And so now you've populated the rest of the fields with the value for the natural log of the concentration of crystal violet. Okay, so I'm going to zoom out a little bit here um, so that I can see things a little bit better, and I can make a graph to see if this guy is linear. And if this guy is linear, then I think I might have a first order reaction. We'll zoom out just a tad there. And to do that, we'll do the same process that we did before, right? We're going to highlight all the time. Always highlight the time first because that's the x-axis, right? If you're on a PC, hold down Control. If you're on a Mac, hold down Command, right? And now you're going to highlight the second column, which is the natural log of the CV, of the crystal violet concentration, like that. Right? Now you have both of them highlighted, and all you have to do is hit the insert button right here, go back over to the graphs over here, and then we want to do a normal scatter plot, right? Wow, that line looks much straighter than the other one. So let's go ahead and let's actually shrink this one down a little bit so it can fit both on the side, like both next to each other. And I'll zoom out a little bit here. Not zoom out, but make it a little bit bigger here, right? And then what I want to do is I want to make this graph look pretty, like I did the other graph, right? And I also don't want to get confused as to which graph is which, okay? So here, of course, we'll change the title. And this, instead of it being 1 over the concentration of CV, it will be the ln, or natural log, of the concentration of CV, right? Versus time, okay? I'm going to go ahead and just make that bold so I can see it better. I'll click on that chart title, hit bold, and I forget what this. I like to keep all my stuff the same. So this other chart here had a font of 16 point font, so I'll change this one also to 16 point font. It's all about consistency when you're making graphs. The other thing I don't like too, remember, is I don't like these grid lines on here. They don't look pretty to me, so I'm going to get rid of those. That looks great. Okay. And then I'm also going to go through and change, I forget what the font is for these numbers. They were 12 and bolded. So I'll go ahead and do that. 12 bolded. And you notice here we're in the negatives. That's why the x-axis is up here right now. And then we'll do that too, bold. And then 12. Right, now we can definitely see that a little bit better. Okay, we can see that just a tiny bit better now. And then you can go ahead and put in your axis labels too, right, to make it all look nice. Oh, well, actually, let's change the lines of the graph, right? The lines of the x-axis and the y-axis still look a little thin. So I'll click on that. I'll click on the x-axis like so, right? And when I do that, it takes me to the format access options. I can go over to this paintbrush here, and then I can move it up to 1.5. I can also change it to black, so you can see it better. And then I'll do the same thing with the y-axis too. 1.5, and then make it black. Okay? And then now I can go ahead and click on the entire graph and add in the uh, axis labels, right? By clicking on chart design at the top there, right? And then going over to add chart elements, axis titles, the primary horizontal, and that will be time again, of course, in seconds. There we go. And then I'll delete the default that was already there, right? And I've already forgotten what I have this set at, so I'll click on the first graph, and I have that set at bold and 12. So I'll change this to also bold and 12, right? And then I can also do the same thing for the y-axis as well. Click on the y-axis there, go to chart design, go to add the axis labels. Now you're doing the primary vertical, and when we do the primary vertical here, the other thing you can do is just highlight this whole thing and go backspace, and then you can just type in what you want. So it would be ln of the concentration of CV, like so, right? And then of course I remember now that it was, I believe, 12 and bold, so I'll go back home, bold it, and then change the font to 12. Okay, so that looks nice. That looks nice. Actually, I don't know why. Well, that looks smaller to me, and that looks smaller too. 12. What did I put for this one? Also 12. Yeah, it's all the same. Okay, it just, maybe it's an optical illusion. Okay. The other interesting thing here too is that uh, since we're below the the um, the zero mark on the y-axis, we have the x-axis sitting at the top there, and that's kind of annoying. I mean, maybe there's a way to get that to go down, so maybe I can have it at the bottom like a normal graph, um, and uh, and stuff. So if you go over here to the axes options, right? Right now, the vertical axis crosses is automatic, so it's going to do at 0, 0. But let's say I wanted to cross at, say, let's do -16. Oops, that's wrong. I did that wrong because this is for the where it crosses at the x on the x-axis, right? So let's switch that back to automatic. So maybe what I want to do then is click on this one here, the y-axis, right? And now I'll change the horizontal axis crosses is here at -16. And that should bring my axis down so that my graph is above the line. My data is above the line. So -16. Oops, that's 19. That's a little too much. Like that. And there we go. See, now that looks like a normal graph again. Okay, so next thing to do is actually get the data that you need out of the graph, because I just spent a lot of time just making the graph look nice, but that's important to me. So when you click on the data, right, it highlights the data. You can right click on the data now, and you can do add a trend line, excuse me, add a trend line. And when you do add a trend line, That line looks pretty straight. We'll also do the equation and the R squared value there. We'll pick it up and move it up here a little bit so we can see it better. And then I don't remember what that font was at, bold and 12, so we'll change this font to bold and 12. There we go. And take a look at that. This R squared value down here is much better than the R squared value I had up there, right? Up here, for the 1 over the concentration of crystal violet, my R squared value was 0.9643. But down here, the R squared value is 0.9891, right? So this R squared value is far closer to 1 than the R squared value is far closer to 1 on the ln of the concentration of crystal violet graph than it is on the 1 over the concentration of the crystal violet graph, right? So just based on that alone, I can tell you, or we can say, that the reaction order for this reaction with respect to crystal violet, right, one of the reactants, is first order. Because when you have an ln concentration or a natural log concentration of crystal violet graph being linear, it means it's first order, right? As opposed to it being second order, because if we're second order, the 1 over the concentration of crystal violet would be linear, right? But since we have the ln, or the natural log of the crystal violet, is linear, we know then it's a first order reaction, okay? We know that it's a first order reaction. The other thing you need to do too is you should also make sure it's not a zeroth order reaction. And the way you do that, right, is I'm running out of room here, right? But it's quite simple. All you do now to figure that out, to make sure that it's not a zeroth order, is you graph the time versus just the concentration, right? Because when you have a graph versus a graph where it's concentration of CV versus time, and that line is straight, it means it's zeroth order. So then when you do this, and you've already figured out that it's going to be first order, if you do the graph for concentration versus time, that should be curved. And if it's not curved, then maybe you did something wrong, right? Because only one of these lines should be straight, and it's the one for uh, the first order data, which is the ln over the ln over the concentration, or the natural log over the of the concentration of CV. And just for shit giggles, we're going to try it real quick here, right? So let me go ahead and highlight here for the time one more time. And then I can scroll up to the top, and this time, instead of doing the 1 over CV or the ln of CV, we're going to do just the concentration by itself. Remember, hold down Command and then highlight the other one, like that, like so. And now all you have to do is graph that. We go to the Insert thing and go over to our scatter plot. Click on Scatter Plot, and we'll pick the very first scatter plot, right? And take a look at that, right? This plot is also curved. Okay, this plot is also curved. So I'm just going to move everything over just a little bit here. This plot is also curved. Okay. So I'll go ahead and change this chart here, the title, which is going to be just concentration CV versus time, right? And of course, I like to make it pretty, so I'm going to go ahead and highlight that, go back to home, and make it bold. And I believe I made that one 16. Okay. The other thing I like to do too to make things pretty on a graph is I like to get rid of these grid lines, right? Okay. I like to make the font thicker and also bigger, so we'll change that to bold and 12. And then again down here for the x-axis, bold and 12. Okay. We also like the axis lines to be thicker too, so I'll change that to 1.5 and turn it to black. Also for the y, sorry, that was the y-axis. Doing this with the x-axis as well, change that to 1.5 over my chart, my axis options, and changing the color to black. Right, that looks great. And then I'll go back to chart design and go into add elements. I'll add an axis title. The horizontal title again, of course, is time. Whoops, I don't want to put that in there. Didn't mean to do that. There we go. Highlight that. Type in time. Whoops. Time. And then the unit right there. And so I'll highlight that whole thing and I'll bold it and make it 12, I think. Yes, that's right. Somehow I got a line here, a square put around my box. I don't like that, so I'm going to have to remove it. We do remove the border there. We remove that border box there by clicking no line, and that makes it go away. I must have accidentally done that when I was clicking over here earlier and typing in weird things. My bad. Then we can go ahead and do the y-axis the same way too. Chart design, add elements, axis titles, primary vertical, and this time it's going to be, and just to make sure it goes away when I'm doing it, highlight the entire default that's there, and just type in the concentration of CV, which is that. And that's going to be in molar. So I'll bold that and also change it to 12 so we can see it better. Nice. So now that all the aesthetic stuff is done, it looks very pleasing to me, right? It's very pleasing. I'm going to just shorten up this graph just a tad so we can fit them all together. You can see them all evenly. I like an aesthetically pleasing graph, so I expect that your graphs will be also aesthetically pleasing as well when I grade them and you turn in your report. Okay, so the next thing to do, all right, is actually get the data you want from this graph. Remember, the way we figured out that it's actually not a straight line is by looking at this r squared value. I mean, just looking at that, you know it's not straight, but just to make sure, we'll right hand click on that thing there and go add trend line. And then the trend line is there, and then we'll just add on the equation and add on the r squared value. We'll move it up here just so we can see it a little bit better, and we'll bold that and turn that to 12 just so we can see it better as well. And notice that the r squared value for the concentration versus time plot is 0.852. That's definitely not a straight line. That's far from straight, right? So that's how we know that it's not a zeroth order reaction. Okay. We had a r squared value of 0.96 for the 1 over the concentration of crystal violet, right? Which is kind of close to straight, but not close enough. So we know it's not going to be a second order reaction. And lucky us, when we did the graph for the natural log of the concentration of crystal violet versus time, that turned out to be a pretty straight line with an r squared value right here of 0.9891. Okay. So what I expect for you to do for your data, specifically your data and results, your results section of your report, right, that you're writing, is I expect to see this data and these charts, right, as well as seeing a graph for every one of the trials you did, right? So there should be 3 graphs for the trial, for the first trial of the 0.05 molar concentration reaction. And then there should be another 3 graphs for the second trial of the 0.05 molar concentration. And then there should be 3 graphs of the the 0.1 molar sodium hydroxide concentration reaction that you did, right? So it's 9 graphs total, right? It should be 9 graphs total, right? Each trial should have its own concentration versus time graph, 1 over the concentration of crystal violet versus time graph, and then a natural log of crystal violet versus time graph, right? And as you make all those as you make, yes, you are making lines, but as you make all those graphs, you'll see that every graph you'll make will be consistent with one of the reaction orders that you've already decided before. For example, for this one, in my data that I'm using here, I figured out that since the ln concentration of crystal violet versus time is the one that has the linear line or the straight line, right? As I go through the rest of my trials and do all the three graphs for each one of those trials, I should come up with the same thing, right? I should also have a straight line for the ln over the ln of the concentration or the natural log of the concentration of crystal violet versus time graph for both the second trial for the 0.05 molar concentration sodium hydroxide reaction and the only trial we have for the zero point 0.1 molar concentration sodium hydroxide reaction that we did, right? So remember, three graphs total, okay? So now that we've done that, right, we need to go through and figure out how to complete some of our discussion questions that we have that are at the end of the graph that will help you actually write your discussion section of your report. Okay, so to do that, this is a lot of work, so I'm going to go ahead and save this here. Saved. Okay. And then, so I'll bring back up the whiteboard here. We'll maximize the whiteboard like so. We'll maximize the whiteboard. Okay. And I'm gonna go ahead and delete all this stuff here because we don't really need it anymore. I don't think. All that's highlighted now. Delete. Okay. So looking at the discussion questions, on the report, not on the report, but on the lab instructions, right? Handout. The first question it asks you is to show your calculations for the dilute concentration, your calculations for the dilute concentrations of sodium hydroxide. Now, the reason why we have to do this is because remember, you were given a bottle of sodium hydroxide, two bottles actually, and those two bottles were um, those two bottles were one was one was a bottle of 0.05 approximately molar NaOH, and then you had another one that was approximately 0.1 molar NaOH. Remember though that you had more numbers back here, okay? Yours all both of these concentrations that you had actually went out to four decimal places, okay? So make sure you include that in your concentrations, or sorry, not your concentrations, but your calculations, right? So because your calculations will be off if you don't do it correctly, okay? So the first question is show your dilute concentrations of the show the calculations for the dilute concentrations of NaOH. Well, you're thinking to yourself, whoops, I didn't mean to make it that small. Sorry. You're thinking to yourself, I mean, I have concentrations already here. Why do I need to make, why do I have to do calculations to make more concentrations, right? To figure out more concentrations. Well, the reason why is because you remember, right? Part of the experiment was that you had these 7 mils of crystal violet. Violet? No, that's not right. Violet. Oh, actually, I have an eraser, so I can just erase that. Cool, cool. Right? Crystal violet. Okay. And you added 1 mil of the sodium hydroxide to the reaction. Right? Remember, the 7 mils of crystal violet came from the burette, right? And then the 1 mil came from that dropper bulb thing, that pipette with the big blue bulb that you did, right? So now that you've diluted this 1 mil of sodium hydroxide with 7 mils of crystal violet, you got to give me a new concentration for NaOH because it's no longer what these original numbers were, right? So how do we figure out what that's going to be? How do we figure out the concentrations, the new concentrations? Well, we have an equation that we learned back in Gen Chem 1, M1V1 equals M2V2, right? And what that means is that we have an original concentration here and the volume that was used, and then we have the new volume, right? And then we can solve for the new concentration, which is M2. Okay, so let's do this. For the concentration of OH minus, right? We originally started with one of them was, approximately. For me, it was just 0.05, but for you, it's just approximately because you had more digits after that, right? Molar. So the concentration then, if we're using our M1 V1 M2 V2, or it's going to look like this. Our equation's going to look like this: 0.05 molar, right, for the original, and then 1 mil for the original volume, and then we just have M2 that we're solving for times a total of 1 mil here plus 8 mils here gives you the final volume of, not 8 mils, sorry, 7. 7 mils here gives you the final volume of 8 mils. So that's your new volume. And all you have to do now is solve for M2. And that's your new concentration of crystal violet. New concentration of sodium hydroxide, right? So doing that math, we get a M2 equals 6, oops, not 6. That's not our 6. Let me erase that. Gives us a concentration then of 6.25 times 10 to the negative 3 molar. And of course, this is the after dilution solution. Ooh, that rhymes. That rhymes. We'll do this again for the NaO or for the OH hydroxide ion of 0.1 molar concentration, but for you it's going to be 0.1453 something. I don't know what it was. For you, everybody had a different number. Right, so we'll start this out again the same way we did before. Instead of putting 0.05, we're going to put 0.01. Sorry, instead of putting 0.05, we're going to put 0.1 molar. That was also 1 mil. And that equals M2. We're solving for M2. And then the final volume again is 8 mils. We'll do all that math to solve for M2. If you forgot how to do this, all you have to do is divide both sides by 8, right? And then that cancels out the 8 on the right side, the 8 mils on the right side. I'll just go ahead and do it just so that um, no one gets confused. We want to get M2 by itself, so we'll divide both sides by 8 mils, like that, okay? And so that cancels out the 8 mils on that side. All you're left with is M2, except that it shrank, sorry. There we go. All you're left with is now M2. And so M2 is equal to 0.1 times 1 divided by 8. Okay? And so M2 then equals, after we do that math, 1.25 times 10 to the negative 2 molar, right? After dilution of the solution. Ha, made it funny again. Okay? So those two numbers are going to be very helpful right here. This number right here is going to be super helpful. Okay, I don't know why I did that. Let me erase that weird mark I put right there. There we go. And then this number right here is going to be very helpful. Okay, very helpful. So that answers right there number on your thing on your discussion questions. That answers number one. Okay, that was number one of your discussion questions. Okay, so let's try to figure out number two from the discussion questions in our lab. It asks the question, show your calculations for the determination of the X value for sodium hydroxide, right? Well, what is the X value? I mean, like actually, what is it? So this is number two. And for number two, or just in general, the rate law is the rate constant times the concentration of A to the X, B to the Y, right? And in our reaction, the A here is the sodium hydroxide concentration. And for the B here, that's talking about the crystal violets concentration, right? The crystal violets concentration. And we actually already figured out what y is in this exponent right here because these exponents, x and y, are both the orders of the reaction with respect to either the hydroxide or the CV, the crystal violet concentration. And we already found out that the y, or the reaction order, with respect to CV, crystal violet, was 1. Remember, we did that with the graphing on Excel, right? And we found that the graph of crystal violet with the natural log of the crystal violet concentration versus time was the one that was linear. And since it was that one that was linear, that corresponds to a reaction order of 1 with respect to crystal violet. So now what we need to do is solve for this x now, right? And what we're solving for here in this x is the reaction order with respect to the hydroxide concentration. And realize that we could have, if we had in some way detected hydroxide concentration during the reaction progress, we could have just used the graphs to figure out what the reaction order is for the hydroxide concentration, right? For the hydroxide reactant. But there was really no way to detect the decrease in hydroxide as the uh, the reaction progressed because hydroxide is actually transparent. It's clear in the solution, right? The reason why we were able to do it with crystal violet is because crystal violet was purple, and as the crystal violet concentration started to decrease over time, the concentration started to decrease over time. You saw that borne out when you were using the Spec 20 and watching those numbers go down over 30 minutes, right? So how are we going to do this then? How are we going to solve for x? Okay, and luckily for us, we have a lot of the things we need already from the graphs and everything else from the crystal violet information data, right? So recall that, and I said this just a second ago, right? When we have a linear graph of a natural log of the crystal violet, right? If that's linear, then that means that we have a first order reaction, okay? And that's where this comes from right here. That's where that comes from. But wonderfully, we know that the pseudo rate constant, which is k prime, right, actually equals the slope of this graph right here. The natural log of the concentration of crystal violet by time versus time graph, right? The slope of that graph, since it's the linear one, right, is equal to the pseudo rate constant, or k prime. And it's not just the slope, it's actually got to be the absolute value of the slope, right? So remember, whenever you write out when you draw two long lines on either side of some kind of variable, right, or number, it means absolute value. Just to make that clear, I'm going to erase this underline I did right here and this underline right here. So it doesn't look like I drew a box, right? What I'm saying here with those two lines is that this is an absolute value, okay? Absolute value, okay? So that helps us out a lot, right? That helps us out a lot because now we can do this equation here that we talked about in class and was discussed in the lab background, where the pseudo rate constant, or k prime, from the uh, second reaction you did, the one that had the one that you had the zero point 0.1 concentration of sodium hydroxide. Sorry, right there, miswrote. Let me fix that. So that was the second reaction you did, or what we called in the reaction, or in the lab, the part 2 of the experiment, right? So the pseudo rate constant, or k prime from, oops, sorry about that, k prime from part 2 over the k prime in part 1, and that was the part of the experiment when you used the sodium hydroxide that was a 0.05 molar concentration, right? Actually equals the concentration of hydroxide from part 2 to the x, all divided by the concentration of the hydroxide from part 1 to the x. Okay? And remember that these two concentrations are not just those concentrations that you had given to you, right? Because you diluted those, right? And you did the dilution calculation in the previous question, right? Where you did the M1V1 equals M2V2 because you took 1 mil of that given solution of sodium hydroxide and you diluted it to 8 mils, right? So the numbers that should be going there are actually your diluted concentrations of sodium hydroxide. So for me, right, in part 2, which is the second half of the experiment, right, where we used the 0.1 molar sodium hydroxide. When I did the calculation, the M1V1 M2V2 calculation to get the diluted concentration of sodium hydroxide, I got 1.25 times 10 to the negative 2, right? And then, so this is my part 1 right here, right? Or sorry, this is my part 2, okay? And then on the other side, or on the other side of the division line, goes my calculation for when I diluted the 0.05 molar sodium hydroxide, right? That's from part 1. And I calculated that previously in the previous question. And that was the 6.25 times 10 to the negative 3, right? And that was part 1, okay? So quite simply then, this number right here, the 6.25 times 10 to the negative 3, gets plugged in for that number there, for the hydroxide concentration there. And then this number here, right, the 1.25 times 10 to the negative 2 gets plugged in for that concentration there, okay? For that concentration there. So we have those figured out. Now, where do these numbers come from, right? Well, like I just said a second ago, the K prime, or the pseudo rate constant, equals the absolute value of the slope from the linear graphs, right? The absolute value from the slope from the linear graphs. So let me go back to look at my stuff, and it turns out that if you recall, I'll show you my Excel file here. So if you look at my Excel file, what my second slope, right? My second part slope here was based on my y equals mx plus b equation for my graph right there, right, is negative 0.0798, right? So that's the number that goes in the top part because that's my part 2 number, my part 2 slope, okay? So we'll go back to the calculations. So I'll write all these out now here to the expression that we need to actually evaluate here and solve for x4, right? So this part right here, the k prime, or from the part 2, or the absolute value of the slope, right? The slope was actually negative 0.0798, but since it's absolute value, it's going to be positive 0.0798. Okay, and that's divided by my slope, the absolute value of my slope, or the k prime, right? From the first part of the of my experiment, right? So I'm not going to switch over to show it to you there because you know where to find it now. And that number for me was 0.426. Now, you're not going to have the same numbers as I have, right? Because my data is, again, fabricated, but it should at least show you how to do these calculations. So all that now equals 1.25 times 10 to the negative 2 to the x, all over the 6.25 times 10 to the negative 3 to the x, right? So quite literally, you can just go ahead and do this math, right? And this number here, the 0.07898 rather, divided by 0.0426, that actually equals 1.87, okay? And then on this side, 1.25 times 10 to the negative 2 divided by 6.25 times 10 to the negative 3 is actually 2, right? But we still have to the x, so don't forget that part right there, okay? 2 to the x, okay? Now, if you remember from algebra, right, and our little like crash course, I like to call it, that we had in class about some basic algebra that we use. Okay, the way that you undo a uh, uh, a number to the x, right, so that you can get the x by itself, right, is you use the natural log, right? So I can take the natural log over here. Whoops, I don't know why I did that. Looks like I put an h there. Shouldn't be an h. So you take the natural log of the 1.87, right? And then I don't have any room there, so I'm just gonna, well, actually, maybe I do. And then you take the natural log of all that too, as well, right? Of the 2 to the x. All right, that's great. Okay. So the natural log does a couple of different things. It undoes the exponentiation, number one, right? But then you can go through and divide both sides by the natural log of 2. And here is also the natural log of 2, right? And so now the natural log of 2 is canceled out on the right side, leaving you with the uh, the x. And then on this side, on the left side, I'm just going to try to make it so it has consistent, um, make it so it has consistent significant figures, right? So now you have x by itself, and that equals the natural log of 1.87 divided by the natural log of 2, right? And I'm one of those that likes to write it so that what you're going to get is this. After all those cancel out, you'll get this 1.87 divided by the natural log of 2.00 equals x. Okay, but I'm one of those guys that likes to make the x on the left side because I can say x equals something. I don't like saying something else equals x. I like to say x equals something. So I'm just going to switch it around. It still means all the same thing. The natural log of 187 divided by the natural log of, oops, not 1 something, but 2.00. Okay? So that equals then, when I do that math, 0.625, oops, forgot the 6 in there, 0.625 divided by 0.693, and then I'll finish that math off and we'll get 0.903. Okay. Now you're supposed to get a value for x that's an integer, right? Either 0, 1, or 2, right? But sometimes there's experimental error, or maybe there was like a little volume mix-up or something when you're actually doing the experiment itself. We were using those pipettes with the blue bulbs that are very difficult to deal with, So a little bit of experimental error is expected. So when you get something close to 1 like this, right, you can just say then that x equals 1, right? And so that means then that since x equals 1, the reaction order with respect to sodium hydroxide is also 1, right? It's the same as uh, the reaction order with respect to the crystal violet, right? So what happens is that what this tells you is that whether you're doubling the concentration of hydroxide or you're doubling the concentration of crystal violet, both of those actions will have the same effect, which is doubling the rate of the reaction. And that's what it means when you have a reaction order of 1 for either of those reactants, right? So let's keep on moving forward. We're going to go ahead and answer now, or figure out how to answer number 4, right? Number 3 just says using the Excel file, plot all your graphs, the trend lines, and figure out your slopes and all that. But we already did that for like way before we even got to the before we got into the discussion question. So we'll skip number 3 since we didn't really skip it. We've already done it. So we'll go to number 4 now. Okay. Oh, sorry. Let me pick the drawing tool there. So here's number 4. Number 4 says, what is the value of the pseudo rate constant and the rate constant? Well, you already know what the value of the pseudo rate constant is because we figured that out using the slope of the crystal violet, right? The linear graph of crystal violet. So knowing that, we can use this equation to figure out what the actual rate constant is, the true rate constant, not the pseudo rate constant, right? So K prime, or the pseudo rate constant, equals the rate constant times the concentration of sodium hydroxide to the x. Okay, and we actually have all these values already. Okay, we have all these values already. We have the pseudo rate constant, we have the concentration of sodium hydroxide, and we have the reaction order, right? These are the 3 things that we already have. The thing that we're solving for now is this, the actual rate constant, or the true rate constant, right? Well, we can do some quick math to rearrange things around so that K, or the rate constant, is by itself. Okay, I'm gonna write it down here again so we can see it clearly. It's just the same thing twice. Oops, I don't know why I put that 2 zeros there, 2 O's there. There we go. That to the X, right? We can divide both sides by the hydroxide concentration to the X, the hydroxide concentration to the X, and we see that all this stuff here cancels out on this side, on the right side, leaving you with a K. And then on this side, we have the pseudo rate constant divided by the concentration of hydroxide to the X. And again, you know me, I like to switch things around so that my thing I'm solving for is always on the left-hand side. So the rate constant equals the pseudo rate constant divided by the concentration of sodium hydroxide to the X. All right. Okay. So we're going to have to do this. We're going to have to do the rate constant then, right, for both parts. Okay. For part one with the sodium hydroxide that was at the approximately 0.5 concentration starting out, and then part 2, which was the sodium hydroxide concentration that was at zero point 0.1 starting out, right? So here's part 1. We can just start plugging things in. I don't know why I said part equal. I meant part 1. Okay, and here part 1. The rate constant equals our slope, right? Our the absolute value of our slope, or our pseudo k value, pseudo rate constant, or k prime value. And for part 1, for me, it was a positive 0.0462, and that was divided by my diluted concentration of sodium hydroxide, which was 6.25 times 10 to the negative 3, right? So that's all that's there, right? And now we have to, don't forget about the x, right? And our x was 1 for a single or first order reaction. Okay, so these numbers right here I used here are from my first part, right, where the sodium hydroxide reaction started out at approximately 0.05. So we can just do that math real quick. Anything to the 1 is itself, right? And then it will be the 0.0462 divided by the 6.25 times 10 to the negative 3. And then when you do that math, K equals 7.4 approximately. And then the units we're using here is liters per mole minute. Okay, I'll do this again for part 2, which is the sodium hydroxide concentration reaction at 0.1 molar. And so K equals the pseudo rate constant from that reaction and the pseudo rate constant from that reaction, or the positive, the absolute value slope from that one is a positive 0.0798. Whoops, that doesn't look like an 8 or a 998. All right, same thing as before, except this is going to be the diluted concentration of sodium hydroxide. So that was 1.25 times 10 to the -2. And then our reaction order X was 1. Okay, and I'll do that quick math. And K equals then 6.4, approximately 6.4 liters per mole minute. And that, my friends, is how you solve for the rate constant with respect to, not the rate constant with respect to, but the rate constant for the reaction, right? Because remember that our reaction, right, rate equals K, concentration of hydroxide, times the concentration of crystal violet, which I don't remember the formula for crystal violet, so I'm just going to put in the abbreviation there, okay? And just as a quick review, remember, we found out that the reaction order was 1 for both hydroxide and crystal violet, right? And so that's why our exponents there and there look like they're non-existent, but when there's nothing there, it means it's a 1, right? And so that's how we solve number 4, or that's how we figure out the answer for number 4 in our discussion questions. I expect you to be able to discuss that kind of thing with me in the discussion part of your report, okay? And then the last question says, obtain the rate constants from your classmates and compare your results, right? Uh, you all did the same experiment, so you all should have very, very similar numbers. And when you compare with your classmates and you have drastically different numbers, then you need to be able to tell me why that happened. What are the possible errors that could happen? Don't just say that it's human error. I want to know exactly what kind of error you're talking about, right? And all that stuff needs to be discussed in your discussion section of your lab report that's due on October 20th, right? And that's it then. If you have any other questions, just let me know, and I will see you on Monday.